So welcome everybody. Welcome to this second webinar that we put together as part of AESQ. And this is focused on process failure mode and effects analysis as defined by AS 13100 and Reference Manual 13004. So just for information, we are going to record this webinar, and we will make it available on the AESQ website in a couple of weeks' time. If you've registered for this event, you will get an email telling you when that has been made available on the website. Okay, so on yesterday's webinar, we covered the requirements that are in 13100 related to FMEA and control plans and how it links into APQP and PPAP. We also give a high-level overview of what we expect to see in a process FMEA. So in today's session, we're going to take a bit more time to step through a process FMEA using the information that's in Reference Manual 13004 to try and bring it to life and highlight what it is we would be looking for to demonstrate compliance. So it's a much more detailed walkthrough, and we will highlight some of the best practices and also some of the things to avoid, some of the common mistakes that we see when we review process FMEAs today. And tomorrow, at the same time, we're going to look at reference FMEAs, which is a great way of building on knowledge that we've already had from using process FMEAs in the business and using that information in an intelligent way so that we can actually reduce the time it takes to create new process FMEAs in the future. And the next thing we will cover at tomorrow's webinar is how we can use a lot of the information from the FMEA to actually create the control plan. And we'll show if you've got the right types of software. Actually, a lot of that can be automated. So again, it reduces the engineering time required to produce the FMEA and also the control plan. Okay, so I know if you joined yesterday, we did a bit of an introduction for anybody that wasn't on yesterday's webinar, just to explain who I am. I'm Ian Riggs. I'm the Quality Executive for Civil Aerospace Assembly and Test for Rolls-Royce in Derby. I've got 16 years experience working for Rolls-Royce, and before that I worked in the automotive industry for a company including Cosworth High Performance Engines. They were owned by Audi AG, and previously you might know a company called Harman, who do all in-car entertainment systems based in Indianapolis. So that's where I really came across FMEA and APQP for the first time, back in the early 90s when Ford, Chrysler and GM were rolling out something called QS 9000, which was the first industry-specific standard based on, at that time, it was ISO 9000. So very similar to what the AESQ was trying to do with AS 13100. I've been with the AESQ since it was started back in 2013, and I've served 2 terms of as chairman for that group. But also I've led the writing teams on 13100 and 13003, which you may know is the measurement systems analysis standard that we published back in 2015. And I'm currently the team leader for the 13004 subject matter interest group. And we'll cover that a little bit more about exactly what that is. The other thing I wanted to share on this webinar is, as part of Rolls-Royce's Zero Defects program, I've had the privilege of sitting down with over 1,500 leaders, both in Rolls-Royce and our supply chain, to talk things like APQP and FMEA, and to understand some of the issues they perceive there are with this tool, and also some of the best practice and some of the opportunities that it's also brought. So I'll hopefully reflect some of that in what we talk about today. But I'm also being supported by two colleagues, Becky Lemon from SAE and Rudolf Braunrieder from MTU. So Becky, could I ask you to introduce yourself and how the polling system is going to work?
Sure. Hello, everyone. My name is Becky Lemon. I'm the Industry Program Manager for AESQ here at SAE International. I will be running the polling today. We're going to use Slido polling, which is a polling platform. Based on yesterday's polling, we figured that about 50% of the attendees have access to it from what I could see. So if you can't, that's okay. We are sharing it on the screen. For anyone that can vote, please do so. It is an anonymous polling feature and it will go away once we're done. So thank you.
Thanks, Becky. And Rudy?
So, hello everybody. It's Rudolf Braunrieder from MTU Aero Engines in Munich again, like yesterday. Second day, and also today I will handle your questions and statements. So please use the chat function for this purpose. I will collect your questions and Ian will answer them during the period provided for that. Same procedure as yesterday. So, and any questions not answered here will be answered later on the website, like Ian mentioned that. So thank you and have a successful webinar.
Okay, thanks, Rudy. So just to share, who do we have on the call? We had over 740 people register for this event, which is absolutely fantastic. We've got people from all quarters of the world. We've got people who are just waking up in the morning. We've got people who are just getting ready for bed. We've got 250 companies represented from 27 countries. So it's, you know, a fantastic response. We're really pleased to be able to offer this webinar to you all. So for the people getting up and for the people staying up late and everybody else in between, thank you very much for joining. And I hope you find today's webinar really useful. To give you an idea of the sorts of companies we've got online at the moment, you can see we have the airframers, Airbus, Boeing, Lockheed Martin, and Sikorsky. We've got the AESQ members, so GE, Safran, Pratt & Whitney, Rolls-Royce, and a whole range of suppliers from very large international companies to some of the smaller SME type companies as well. So I haven't been able to find all of the logos, so I just wanted to give you a sense of some of the companies that are on the call today. So what we're going to cover in this overview, as I said, we're going to step through an FMEA from left to right, and starting with, you know, how we define requirements all the way through to the improvement actions. Now we will take a 5-minute break halfway through. We estimate this is going to be slightly over 2 hours, so maybe 2.5 hours in duration. And as I said, there'll be times for questions as we go through and at the end of this session. So just to make the point, normally we would show this video, but Webex has been playing up and we don't want to have this video stutter through. But if you go on the AESQ website, you will get access to this video. And what you will see is it shows how a lot of the different standards and how the different quality tools actually work as a system. So all the way from design FMEA to process FMEA to control plans, capability, measurement systems analysis, process control and beyond. It's a great 3.5-minute video that shows the value of these tools as a system. Now today we're going to be very much focused on process FMEA. We will touch on some of the inputs that we need and some of the outputs, but very much we're going to be focusing on the process FMEA. But I would, if you haven't seen the video, seek it out and you can either watch it on the website or download it and share it within your company. So let's begin. So the first thing I just wanted to point out is a general comment. For the purposes of the webinar, we're going to show you some FMEA templates and some examples using very short text. Now, one of the things we need to think about is this process FMEA potentially is going to be a live document for 20 to 30 years. So the team that creates it is not going to be the same team that needs to maintain it over that duration. So the precision of language we would use in an FMEA is really important. One, because it has to be read by somebody else and understood what the intent of that comment was. But also, as we'll see later on, and as we covered yesterday, each statement in one column leads to a corresponding statement in the next, and how we write that statement, the accuracy and the precision of that language, if it isn't done correctly, could actually lead us off in the wrong direction. And we'll see some examples of that as we go through today. So one of the things to always challenge ourselves on, anything we put in an FMEA, if somebody was reading it without any of the background of the actual part we're looking at, would they be able to understand it in the same way as the team that's creating it? So let's start at the very left-hand side. It's the operation and step. Now this is really important because we see lots of times where maybe things have been included in the scope of an FMEA that don't need to be there. So within 30,100, we've really tried to specify the things that we need to consider. So we say we want every operation and every step included. When you get into the detailed steps though, we only want those steps included that are going to transform the product. So in other words, if you're going to drill a hole, you're transforming the product. But it could be unintentional things that could happen that would also lead to the product being transformed. So things like storage or transportation has the potential for damage or to have FOD. So those things need to be considered within the FMEA too. And that might lead you to design a different storage system, design a different transportation method, internal packaging, etc. as a result of that. So those are the steps we want to focus on. If there's something you do that doesn't actually have any impact on the product, I've seen ones where it's complete batch card. Well, that's not going to do anything to your product. So although you can identify lots of ways you could complete the batch card wrong, it isn't actually directly related to transforming the product as such. Okay, so the first challenge for us is to make sure that the operation and the steps that we do include in the FMEA are valuable. So if you take that as the first guidance, let's just illustrate that with a quick poll. So Becky, do you want to just quickly talk us through how the poll works?
I will do that. So I'm going to activate the first poll for everyone. The question should be appearing on your screen. Please proceed to cast your vote. So the question, the PFMEA should consider only those operation steps that can transform the product, even if inadvertently. Therefore, which operation or step should not be included in the PFMEA? You can go through the list there and check those that apply. Looks like everyone's starting to vote.
Now, I should point out, I can't actually see the results from the polling from when I am. So I'm going to need Becky to try to paint a picture with words when the polling stopped.
I can do that. We have 155 people that have voted, 65, 93, 200 people have voted. We'll give it 5 more seconds here. Oh, votes are still coming in. So for drill hole, we show 8%. For
Yep.
assemble part A to part B in correct orientation, we have 10%. Load the CNC program into CNC, 24%. Store parts in warehouse, 33%. Transport parts to assembly line, 23%. And complete the work traveler batch card, 81%.
Okay, so let's have a look at the answer. Okay, so in that example, the question was, which are the things that wouldn't end up directly transforming the product? So if you drill a hole in it, then you're intentionally doing that. So, that is absolutely something that should be in your FMEA. If you're assembling part A to part B in the correct orientation, again, that's a direct, deliberate action that you're doing to transform the product. So clearly that should be in. Loading the CNC program to the CNC, that in itself is not a deliberate action to transform the product. You're not actually doing it. If the product doesn't need to be anywhere near the building when you're doing that. Now, if you load the wrong CNC program into it, that could be a cause of, well, probably a cause of a disaster later on, but it's not it's not a deliberate or an inadvertent thing that's going to transform the product. If you store parts in the warehouse, even though you're not expecting to transform the product, you could inadvertently do it because it could have corrosion issues, part preservation might not be carried out correctly, it might gather FOD because cleanliness issues in the warehouse. And the same with transporting parts to the assembly line. You don't want to transform the parts, but it is open to damage and to FOD again when you're actually moving that part around. So there's a direct connection to that activity and the part quality from the activity that you're doing. And then the last one, complete the work traveler batch card. I'm glad to see that was high, because again, it's not going to transform your product when that's been done. So it's, sometimes you can spend the first 5 or 10 pages going through an FMEA and only seeing load tools into CNC, load the fixture, complete the batch card, do the kit in operation. None of those actually get you to what it is you want the FMEA to be focused on, which is the product quality. Okay, so hopefully that makes a bit of sense. You've got, this is another way of showing it, you've got deliberate transformations, inadvertent transformations, and then no transformation. And it's the no transformations you don't need to put in your process FMEA. The other one where we sometimes get caught up is when it comes to measurement systems. And I've seen 2 common mistakes we can have around measurement systems. So if you take a part and you're creating a number of features, you often see somebody might put down, well, what's the failure mode for this particular hole depth? And so they say, what if your measurement system measures it wrong? Well, the logic would be, well, if you do that for one feature, you now have to include that on all of your features. And that's just going to generate an awful lot of lines where the answer is going to come back, well, make sure it's calibrated, make sure you passed an MSA. So we should avoid trying to put in things like either the measurement system measured it wrong, the inspector got it wrong, because you could put that on every single line item and just generate lots and lots of noise that stop you seeing the real issues. For a measurement system, the real key things where you could legitimately put something into your FMEA is when you load it onto the CMM, you could damage it. It could pick up FOD. It might become cleanliness issues, etc., because you're handling the part. Those sorts of things would be legitimate to have as a line item in there. But the fact that your measurement process needs to be proven capable, there's a whole column about detection control and detection rating in the FMEA for each line item. That's where those things need to be considered. So just a care point, that is sometimes where we get a little bit lost on how we consider measurement processes. Okay, so when we look at defining requirements, we're going to look at three different types. One where you've got geometric tolerances, machining operation. One a material processing, in this case heat treatment, and assembly operations, because the three of these things are quite important, how we understand how the requirements need to be defined in the FMEA. So the simple one is taking an engineering drawing for a machine part and splitting that down into what the requirements need to be. So on this one, we've got a hole drilling operation. It's on a CNC machine. And effectively, what we need to do is transfer all of those characteristics from the drawing into the requirements column. And then for each requirement, we will look to evaluate what's the failure mode, what's the cause, what could go wrong, how do we control it. So in this example, you can see we've got a series of holes. They've all got diameters. There's an X, Y position. There's a depth specification, etc. We'd expect to see all of that listed in the requirements column. Now you might get that from a process flow diagram. Certainly in Rolls-Royce, we use a characteristics matrix, which is a fantastic document that combines almost your process flow with a list of all the characteristics that are created at each operation step. And that's the document we would use to complete this requirements column. One thing to be aware of, I'm sure a lot of you have similar type of products. Many of the products Rolls-Royce machines may have 2,000, 3,000 characteristics on it. And when you come to say, well, we need to include all characteristics in the FMEA, crikey, that's a really big task now to have thousands of characteristics. But there are opportunities to kind of group some of those characteristics together, but there are some rules around it. So if you take this example, as long as the feature is doing the same job as the other feature. So in this case, there's a ring of holes in a part that you're going to put a bolt through to marry two parts together. Okay, they're all doing exactly the same job. They've got exactly the same specification. So the tolerance and the nominal is exactly the same. They're made on the same process. Then we can actually group those together and do the line on the FMEA once, but read it across for all 10 holes. But it's important that you really justify to yourself that this is really the same, doing the same job, and it has the same tolerance, and the consequence, if it was to be wrong, is exactly the same, and we're going to inspect and control it in the same way. If all of those things are true, then the RPN would be the same for all 10 holes. So if we did it 10 times, they'd all come out with exactly the same score. So with a little bit of engineering understanding, you could look at that pattern of holes and say, I'm just going to look at this once and then read across that to the other 9 holes that are included. And that can really help. So, we have some parts with 500 holes, which are all for air cooling, all doing the same job, made the same way. That becomes a single line on an FMEA. But it needs to be done with care. Okay. A more difficult one, and it comes back to the point we made earlier about the precision of language we put into the FMEA. So here's an example of heat treatment. If you look at the work instruction, it says soak parts 350 degrees C for 2 hours. Now, if you're doing the FMEA and that is your requirement statement, okay, what would your failure mode to that statement be? Maybe use the chat function and send some answers. Soak parts 350 degrees for 2 hours. What failure modes, if that was in your requirements column, what failure modes would you get? So incorrect temperature, above, below temp, over, under heat, temperature too high. Yeah, absolutely. Okay, now the only problem with that is yesterday we talked about failure modes must describe a product characteristic. So temperature of furnace too high. If you ever had a non-conformance escape to the customer, your customer will never say, look, I've just received this part. The furnace temperature is too high on it. So it's because of the way the requirement is defined, it leads you naturally to say, well, yeah, I might have put it in there for too long. So instead of being 2 hours, it was in there for 10 hours, or it was only in there for an hour. It was the wrong temperature, it's too high or too low. That would then lead us to kind of say, well, okay, now the failure mode is not a product characteristic, it's a process parameter. And therefore the effect becomes parts too hard, parts not hard enough. Now the effect becomes a product characteristic, not, well, what does that mean to the end user? If that was flying around the sky and it was too hard or too soft, what difference does that actually make? But it doesn't lead us to consider that. And then potential causes you might have, well, the furnace wasn't calibrated, etc. So if we go back to that definition of a failure mode must describe a product characteristic, what we really want the requirements to say is harden material to 45 HRC plus or minus 3 HRC. Now the way we do that is to put it in the oven for 2 hours. But what you're looking for is a failure mode that would be related to what are you trying to achieve at this step. And at this step, we're taking the material, we're trying to harden it to 45 plus or minus 3 HRC. So now we've got that as a requirement. What would the failure mode be? Again, if you use your chat function, how can we get that requirement wrong? Too hard, too soft, yeah. Too hard, too soft, exactly. Okay, so too hard, too soft. That's exactly what it should say. Now we're describing something about the product. So we know what we want is in the requirement. That's the specification that we're trying to achieve. The failure mode is something you can actually measure on the part, on the product. And we say that's going to be, is on this particular one, it's too hard or too soft. Now that we look at the effects, what is the effect of the material if it's too soft? Okay, we've got excessive wear, leads to engine vibration and noise. Excessive wear reduces service intervals. Now we can start to talk about, well, what difference does it make to the product rather than just leading on to more process questions. So it's really important that when we look at the requirements, the requirement should be written in a way that the failure modes actually fall out. So if it's a diameter of 10 millimeter, it's easy to say, well, it could be too big or too small. If it's a length, it's easy to say it's too long or too short. If it's not written in the right way, the failure modes won't fall out, and we can end up with lots of words, but not very much focus on what do we need to do to make this part zero defects. And it's a really important thing to remember with failure modes. Failure modes are finite. If we write the requirement correctly around, particularly around geometric tolerances, there's only so many ways in which that can fail. And once you know that, you can actually use that when we're actually developing our FMEAs. So, if something needs to be, we're going to drill a hole, location X, location Y, how could that be wrong from a failure mode? Well, okay, it could be in the wrong location. Diameter we talked about, it could be too big or too small. But that's the only two things that can go wrong with the diameter. Okay, so I've had people say, yeah, but what about roundness? Yeah, okay, well, roundness isn't the diameter spec. We've got a diameter spec. We might have a separate roundness spec. And therefore, how could we be out? The failure mode is out of round. Depth could be too shallow, too deep. Straightness, not straight. No burrs, we have burrs. No FOD, we have FOD. No damage, we have damage. So if we are really precise with the requirements, we can be really precise with the failure modes, because there are only so many ways in which that requirement can fail to be met. And that's really important, because if you get to a failure mode and you're not describing something about the product, we haven't got the requirement definition right, and we need to go back and revisit it. As I said, normally on things like geometric tolerances, it's very straightforward to take them off the drawing, take them out of the specification, put them in your FMEA. And again, if we look at milling operations, too long, too short, too wide, too narrow, too big, too small, burrs, FOD, and damage. So, one of the things in RM 13004 we spent a lot of time doing was actually developing almost like a library of failure modes for different characteristics. The other thing to bear in mind, when it comes to defining the failure modes, sometimes one trap to avoid is we can say, okay, but the failure mode could be different. So it could be extremely short. What if it was 1.5 inches too short, as opposed to 10 microns too short? Or it could be too long. As a failure mode description, you don't need to quantify how short is too short and how long is too long. Okay, and I'll show you this as an example. So if you take this one, bar length 10 millimeters, it can be tempting to have a failure mode that says extremely short, significantly short, just too short, in spec, just too long, significantly too long, extremely long. And the argument goes, yeah, well, if it's extremely short, you can't fit the part to the subsystem. Therefore, it's almost like mistake proofing, because the part physically won't fit. If it's a bit too short, then you might be able to fit it, and you get an issue with performance or reliability, and therefore the consequence is different. And you can go through all of these and argue that extremely too short is actually better than a little bit too short, and extremely too long is better than a little bit too long, because parts won't fit. It's like mistake proofing. But those examples don't belong in your failure mode column. We'll consider those in the effects column. Okay, so when we come to the effects later, and you say, well, on this product, it's too short, what are all the things that could lead to? Well, it could lead to something very severe on the engine. It might lead to a concession or some rework. The different types of, the quantification of whether it's too short or too long, too wide, too narrow, gets picked up in the effects column later on. So all we need to write in for a failure mode is if it's too short or too long. Hopefully that makes sense. The other thing we should avoid, and we had this yesterday. So yesterday we had a little poll or chat function example where we said, for diameter, what are all the failure modes? And we had a lot of correct failure modes, but we also had some that were starting to get into depth and some that got into position and different things. So it's really important we only link failure modes to a requirement. And it's quite easy sometimes to fall into the trap of, I'm drilling a hole, how could this be wrong? I've got a specification that specifies the diameter and the position. But what if I put, hole not round, and what if there's FOD in there? So you're actually developing failure modes that aren't linked to the requirement. That's where you've got to be really careful with it. If you feel that there's a requirement missing, so maybe you need a straightness specification and the designer's left it off the drawing, that's where that dialogue needs to be, of saying, well, really we could do with a spec for straightness or for parallelism that isn't on there, because that is something we would want to measure and judge. So we need to make sure that we're only discussing the real requirements. We aren't thinking ahead and adding other requirements into that discussion. So on this one, hole not round and FOD present, well, actually to this drawing, they're not required. So there's no need to include them as a potential failure mode. Okay, now assembly, out of all of the FMEA applications, is probably the most difficult. So we've seen on things like material processing, you've got to be really careful with the language, otherwise you could end up going down the wrong path. That is especially so with manual assembly. So, when you're describing fitting parts together, there's only so many ways, anybody that's done Lego models or Meccano or whatever, there's only so many ways you can get it wrong. So it might specify the orientation of the part. It tells you to fit part A to part B. Torquing bolts to a certain value to get a certain pressure and seal. Put in a sealant and a certain amount of sealant in a certain place. And again, we've got things like FOD and damage. But it's really easy to get that requirement wrong. If we don't specify the requirement correctly, we may end up with failure modes that are more process-based than product-based. And again, the sanity check is if you read the failure mode, if it isn't describing something you can physically see or measure on the product, it's wrong. And one of the biggest challenges we've had, certainly within Rolls-Royce, is going back to the requirements column and making sure the information we take out of the fitting instructions is the right information to allow us to get to a failure mode that is actually describing the product. Okay, so again, the same rule on assembly applies exactly the same way as it does on a machining process or a process material processing example. The failure mode must describe something you can see or measure on the product. So in Appendix A of 13004, you will see we have created a failure mode library. It's a good chance to kind of review your own FMEAs and say, are these, do you comply with this failure mode library? So where you're considering a depth, a diameter, a radius, a crew position, does this failure mode library describe the failure modes that you've actually got in your FMEA? And when we come on to reference FMEAs tomorrow, we'll see this in a broader sense, because we will also have a library of potential causes and detection controls, etc. as well. So that takes it to the next level. But remember, failure modes, if we get the requirements right, they are finite and there should be a logical progression from how you describe the requirement to how you describe the failure mode. So another quick poll. Hopefully that all made sense to you. We're going to ask this question. So which of the following are not failure modes in a 13004 FMEA? So you just need to click the ones that are not failure modes as we've just described them. Okay, Becky, can I hand over to you?
You can. So the Slido polling app is open. Please go in and submit your votes in the Slido polling app. Looks like people are starting to vote. So we'll give it about 30 seconds here. About 10 more seconds. Get some more votes in. Okay, we have about a little over 200 people that have voted so far. The votes are still coming in, but for number 1, CNC coolant strength too strong, we have 70%. Number 2, bar too long, 10%. Number 3, wrong drill used, 56%. Number 4, part damaged, 18%. Number 5, dwell time too long, 46%. Number 6, the radii too big, 4%. 7, furnace temperature too high, 49%. 8, no part fitted, 27%. 9, tooling damage, 68%. And number 10, the hole too small, 4%.
Okay. So we've got quite a range of different results. So let's kind of look at the answer then. So the ones which are legitimate failure modes for 30,004 are on the left-hand side. You can see these are all describing things you can see or things you can measure on the part. So the bar being too long, that's a failure mode. Part is damaged, you can see it, that's a failure mode. Radius too big, you can measure it, failure mode. You've forgotten to fit a part, that's a failure mode. And the hole is too small, you can measure it, that's a failure mode. If you look at the incorrect side, if your CNC coolant strength is too strong, that's actually describing something with the process. Your customer will never phone you up and say, you've just sent me a part and your coolant strength was too strong, because you can't see it and you can't measure it. So it's not a product non-conformance. You've used the wrong drill. Now that could sound bad, but it could actually be within the tolerance that you needed. So it doesn't necessarily mean it's going to give you a problem. But if you used the wrong drill and it was the wrong size, then that is going to be a cause of making the hole too big, if it was too big or if it's too small. But it's not describing the product. You can't see that you've used the wrong drill from looking at the part. Dwell time too long, again, is describing a process parameter, not a product feature. Furnace temperature too high and tooling damaged. All of those things you can't see by looking at the product or measuring the product. So that's why it's really important that we are laser focused on if it's a failure mode, it must describe something you can see or measure on the part. The other information is useful, but typically they would end up in a potential cause column, not the failure mode column. And just to explain, these causes aren't linked to the failure modes on the left-hand side. I've just taken the two and put them in a different column. But wrong drill used, that could cause a problem. If you have the dwell time too long, that can cause a problem. So process non-conformance does get picked up in a process FMEA, but it's in the potential causes column, not the failure mode column. So if you take anything away, the one thing that will really help you evaluate your process FMEAs easily is if you look at the failure mode column on your current FMEAs and look at the description that's in there. If it's not describing a non-conformance of the product, then you've probably got the requirements wrong, and everything to the right of your failure mode column is going to be incorrect. Okay, you're going to be solving a different problem to the one we want to solve, which is how do we prevent the process causing this product non-conformance? Okay, so in summary, as I just said, the right failure modes come out of the requirements description. So the requirements description must be concise and precise to allow the failure mode to kind of fall out of that description. It's a particular issue around assembly FMEAs where you usually have a lot of information in the assembly instructions. If you don't take the right bit out to put in your requirements column, you'll end up with incorrect failure modes. The other care point is don't specify different increments of failure. That will come up in the effects column later on, and we'll show some examples later. Don't put failure modes where there's no design requirement. It's an easy trap to fall into, especially when you have a room full of engineers. It's quite easy to identify all of the things that could be wrong with it, even if it actually isn't specified that that's a requirement. And remember, failure mode should be finite. If you can't get one or two failure modes, then you probably your requirements statement is probably too loose and needs to be improved. Okay, so Rudy, we'll take a pause there, and any questions?
Yes, Ian. So a lot of questions coming in. I think it's not possible to answer all questions, but the questions not answered here, as I mentioned before, we will publish the answers later on the AESQ website. So a few questions I think we can answer here. One of them is, so if we make a generic process change that impacts all our products, is it expected that we update all of our PFMEAs?
So it's kind of hard to be definitive without the example, but potentially the answer to that is yes, because that change on product A may have a different effect, may have a different occurrence to something on product B. So as we talked about yesterday, an FMEA should be applied to an individual part number, because the way parts are used in the final product can be very different. They can undergo different environmental conditions, they might be under different pressures. So the severity score and the occurrence score as a result of a process change could be very different. So you should go through and evaluate that. And I always, there's one word associated with FMEAs that always fills me with dread, and that's the use of the word generic. There's no such thing as generic when we come to aerospace parts. So it's really important that if you make a change to a process that you put 50 part numbers, all your part numbers through, where you have FMEAs for those parts, then you should evaluate the impact of that change on that specific part, because I'd be really surprised if the RPN or the risk profile number would come out the same on all of those parts. Okay.
Okay. Another question was following. Do we need to include final inspection in the PFMEA if this operation does not transform the product?
Yeah, so on the slide I showed earlier, final inspection as an operation should be included, but we've got to be really careful of why we are including it. So it is not to say that what if the final inspector misses a failure mode, or what if the CMM measurement system is inaccurate and therefore all of the readings are out. The purpose of including inspection as one of the steps would be to say, is there any way that during inspection I could damage the part, I could introduce FOD, I could have cleanliness issues. So in many measurement rooms, they'll clean the part first and then they'll measure the clean part. Well, okay, there's opportunities, I guess, for FOD, there's opportunities for staining. So those are the things that are unique to that process that could inadvertently transform the product that you should consider. But don't fall into the trap of measurement system measures everything wrong or inspector misses non-conformance as part of the process. Because we know even on capable measurement systems and capable inspection processes, those acceptance thresholds are saying we'll allow the inspector to miss 20% of these issues, or we'll allow the CMM to not pick up 30% of the tolerance. So as long as we avoid that, then absolutely you should include final inspection within the scope of the FMEA, but for only the things that you could end up transforming the product, even if it's inadvertently, like damage, like FOD, like contamination. Okay.
Okay, clear answer. Maybe the last one. What about operations steps that do not create final feature? For example, cone forming prior to welding.
Yeah. So my own personal view is anything that you do, even if it's not creating the final feature, has an opportunity to potentially scrap the part or cause a problem downstream that you hadn't considered. So I would definitely recommend you apply the FMEA approach to everything you're doing. So even where you've created manufacturing drawings for interim stages, you could end up damaging a part that you could avoid if you do the FMEA. You could end up creating features that may cause a machine further down to have a problem, FOD, contamination, etc. So in a world where what we want to do is create the least disruption. As I said yesterday, more than 60% of all our delivery problems come from a quality issue somewhere in the supply chain. That could be caused by a manufacturing tolerance, a not finished part, not finished feature process. So if you want to optimize your process from A to Z, If you want to make sure that you're not introducing additional costs, rework, delays, absolutely you should include everything in your FMEA. Now, the way 13004 is written, it's really focused on those final features. Internally, I think you get a lot of benefit if you make sure you include everything in the scope of your FMEA.
Okay, Ian, thank you very much. I think that's it.
Okay.
The other answers of the other questions we will publish on the AESQ website later on.
Brilliant.
Okay.
Okay, so what we've got
Okay,
one more
fine.
section. Sorry, Rudy, go on. Sorry, Rudy, were you saying something then?
No, it's okay. It's okay. No.
Okay,
I
we're going to do
finished.
one more. We're going to do one more section, and then we're going to have a short 5-minute comfort break. So if you bear with us a little bit longer, we're going to now move on to looking at the effects and the severity of the failure modes. So once we've got our failure modes, now what happens? Well, the effect is there to say, if this happened, so in this example, we've got a hole diameter and it's too big. If this hole diameter was too big on this product, what would the effect of that be? And in particular, we want to consider the effect on the end user. We may have an interim customer. So if you imagine, engine manufacturer like Rolls-Royce, we send our product to Airbus. Airbus will be able to find certain non-conformance. It fits it to the wing. So if there was anything wrong with the parts that allow Airbus to do that with our engine, they would find certain things. They do some ground running of the engines, etc. So there are certain things that our customer would find, but there's another list of things that our end user, the operator, the airline, could find, when it starts to fly it might find it in a year's time or 2 years' time or whatever. So we should be looking at the end user and how could this hole diameter being too big affect them, our customer, Airbus or Boeing, but also, a subsequent manufacturing operation we should also consider to be treated like a customer. So this is where we will now start looking at different levels of failure mode and the potential impact that could have. But every failure mode, you'd expect to see more than one effect. And as we go through it, we'll see the sorts of effects as a minimum you would expect to see listed. If you see a failure mode with one effect, you should be very suspicious. And that's true, I guess, all the way through the FMEA. I mean, you should have multiple effects. For every failure mode, you should have multiple causes. Otherwise, you're going to start to question how well is the FMEA been put together. This is the point. Lots of people say, well, I can't do a process FMEA because I haven't got a design FMEA. That isn't true. What you need is a designer, hopefully informed by the DFMEA, but sometimes DFMEAs don't exist. And for modifications to an existing product, it'll be really difficult to build a business case to get the engineering team back together to do that because the design is already designed. But you can still get the information you need if you've got the designer, hopefully informed by the design FMEA. This is where, out of all of the times, and it's useful to have a designer throughout the process, but this is where their input really comes into play. Because they are the ones who will understand how that failure mode could cause a problem to the end user or the customer. Your manufacturing engineer should understand how that could actually cause a problem further down in the process. But it's the designer you need at this stage. And these are the two bits where that designer plays a really important role. So there's the effect and the severity. So we're going to take this one. as an example. So we've got engine vibration. So the fact that this hole diameter is too big, let's say it's a bracket or something, it's on an engine. It allows, therefore, the structure to move over time, right? As the engine accrues more hours, and that might lead to wear. And if that wear is picked up on the service when the engine is serviced, you may have to replace the part before it's due to be replaced. So let's say it's supposed to do 2,000 cycles. Because this hole's too big, it wears prematurely, has to be replaced after 1,000 cycles instead of 2,000 cycles. It doesn't affect the engine performance, but the fact you need to do that is going to add extra cost to the servicing of that engine, and it could be potentially disruptive to the airline operator, because now they need to take the engine off after 1,000 cycles because it's not going to reach the 2,000 cycles. So the customer will not be happy. The person who can explain how that works is your designer. Now, because the hole diameter is too big, you can't rework it. And therefore, the manufacturing engineer would say, well, if it does come in and it's too big, I'm going to have to scrap it unless I can concess it. So if it was marginally too big, I might be able to concess it, but typically I'm going to have to scrap it because I can't rework it. If the part comes in and there's kind of a precedent set for if it's less than 10% of the tolerance band, you might get an engineering concession to approve it. History and time has told the manufacturing engineering team member that is a potential outcome. So what you've got is 3 very different levels of effect. So worst case, it's going to have half the engine life and the operator is going to be very unhappy. Secondly, you might have to scrap it and build another one. So again, operationally disruptive and extra cost. If it's only slightly out, less than 10%, then potentially you might be able to get an engineering concession if engineering agree to that. So this is where, like we talked about earlier, there's 3 very different levels here for the same thing of hole diameter too big. So when it comes to severity, in 13004, there's 2 potential scenarios where you would use to actually score how severe, how big an impact, how disruptive would this non-conformance be. So the first one, on the left-hand side, you can see severity of effect on the product. Okay, so if the hole was too big, what does it mean for the product? And then you have a list of criteria to look at. On the right-hand side, you're looking at the severity of the effect on the process of the manufacturing plant. And again, you've got a list of criteria, descriptions you can use to try and help you score the right severity. So if we look at the effect on product, most severity scales are going to work something like this. So a 9 or a 10, very severe. In this case, it's a safety issue. And, typically if it's a safety issue, you could end up killing somebody or injuring somebody. Usually comes with non-compliance to regulations, and therefore you would not be allowed to fly that engine because it doesn't comply with regulations. So a 9 and a 10, very severe, probable death, worst thing that can happen. A 1 is nobody would even notice. Okay, so if this hole was too big, in this particular situation, you wouldn't even notice it. And then between 1 and 10, you have different levels of dissatisfaction, whether the product may not work as required, etc. So from those descriptions, you should be able to take the failure mode, the effect, and be able to use that to score how severe it would be. From a process point of view, again, a 9 and a 10 is where the process could end up injuring a person, either with or without warning. And a 1, again, is no effect. And then in the middle, so on this one, you can actually see you've got injuring a person, 9 and 10. You've got scrap at 7 or 8. You've got rework, 5 and 6. You've got rework in cell, 3 and 4. Minor disruption, 2. So everything from you wouldn't notice, rework, scrap, you're hurting somebody. So let's have a go. We're going to do another poll. On this one, so the first one we had was engine vibration can be caused if the structure is able to move due to the oversized hole feature, may lead to reduced component life, engine performance is not affected. So Becky, can you run the poll on this one, please?
So I've opened the Slido poll for everyone. You should be able to see it on your screen now, and you can answer what's the score. Looks like the votes are starting. So we'll give this about 30 seconds or so and get some votes in, and then I will read off the scores. About 10 more seconds to vote. Okay, so number 1 received 1%. Number 2 received 1%. Number 3 has 2%. Number 4 has 5%. Number 5 has 15%. 6 has a big 43%. 7 has 22%. 8 shows 7%. 9 shows 3%. And 10 ended up with 2%.
Okay. So let's see what the answer in this example is. And it's 6. So bit of a clue in the wording. So we've got product operable, but service life greatly reduced. Customer dissatisfied. So we've got on this one, part of the description was may lead to reduced component life. But you can see from the description, if we were to plot out the answers Becky's been through, if you've got a 7 instead of a 6 or a 5 instead of a 6, if you're in that right ballpark, these things are relative scoring that, I wouldn't lose any sleep over that. If you've got a 1 and it should be a 6, or a 10 and it should be a 6, that's a little bit more worrying. But from the description in the product and the description of the effect, we should try to find out what is the closest fit. And if it's hard, that's where we get the designer to come and help us and say, well, on this scoring, we might need to refine the effect description that leads us to make sure we select that. But in most cases, you should be within plus or minus 1 of the scores. Okay. So second one, we run a second poll. So rework is not an option for this feature, and therefore the part will need to be scrapped. So this is now using the process severity ranking. So how would you score this one?
So the poll is open. Poll number 4. Please proceed to start voting. Looks like the votes are coming in, so we'll give everyone another 25 seconds. Another 10 seconds.
Okay, so I can see a lot of consistency on this one. Now, I've scored it as a 7, only because in my little head, I was thinking, well, we make these in batches of 20, and if one was out, then it's a portion of the production run might have to be scrapped. But anybody that's put an 8 is, you know, in your head, you might have said, well, you know, I only make these one at a time, and therefore, for me, it's an 8. When Ian scored it, it was a 7. If it's a 7 or an 8, because it's got the word scrap in there, it can only be a 7 or an 8. Whether it's 100% or a portion, it's only a 7 or an 8. So again, I wouldn't worry too much if you scored it as an 8 and it's a 7, or it's a 7 and it should be an 8. I wouldn't worry too much. So on the last one then, if the oversized condition is less than 10% over tolerance, then it may be possible to apply for an engineering concession. So how would you score this one?
Okay, the Slido poll is open, everyone. Please start your vote. So again, we'll give this about 25 seconds. The votes are starting to come in. So maybe another 10 seconds or so.
Okay, so now on this one, the consequence is raising a concession. So we're not going to scrap it. We're not going to rework it. We're not going to rework it in the cell. So the only, you know, by working through that, it actually brings us down to a 2. It's not a 1 because you're actually doing something as a result of it not being conforming, whereas if it was a 1, you wouldn't need to do anything. But it's not a 3 because you're not reworking it. You're applying for a concession to allow you to ship as is that non-conformance. So really the only description that fits is a 2. Now it is disruptive because concessions take engineering hours, it costs money to process it, but you're not physically having to do anything to that part to bring it back into specification. So in that case, it's a 2. So just to summarize, there should be multiple effects per failure mode. And as we've seen in that example, you know, there's at least one you need to talk about as the end user. There's at least one you need to talk about in terms of the process. You'd expect to see multiple effects per failure mode. This is where you need the designer. But don't fall into the trap to say, well, if you're going to design FMEA, you can't do it, because the designer will only help you with the customer effects. Internal effects, you and your team should know that because of your history and knowing what goes wrong. A DFMEA is a great way of capturing designer knowledge when they design the part, but if you have the designer who understands the component, they should be able to give you enough input to help you score this anyway, even if you don't have a design FMEA. It's important the effects description is clear and concise, otherwise it'll make scoring it really difficult. And always remember, if the severity score is 1, don't see many of those to be honest, but if the severity score is 1, you don't need to do anything else to the right on your FMEA. Okay, so it's not discernible, no one's ever going to notice, you may as well just leave it there. That takes us to questions, but we did promise everybody a 5-minute break. So I make the time 16 minutes past 3. If we have 5 minutes, Please put any questions in. We'll come back in 5 minutes time, and then we'll answer some questions that Rudy can pull together, and then we'll move on to the second half of the webinar. Okay? Thank you.
Okay, and let's do so.
Hi, Rudy. Is that time? I got carried away looking at some of the comments that were coming in, so I've kind of lost track of how much time we
Yeah.
had.
Just
Do you want to
Right
start
on
posing some
track.
questions and we can?
Ian, we have not received any questions, but there are big concerns that the design responsible customer will not provide the potential failure, potential effects, and the severity per characteristic or per failure mode regarding flight operations. So these are really big concerns.
And I think.
So if so, what can a supplier do?
Okay, so I think it's really important that the conversations with the customer and the design authority take place. So I'll give an example. We, as I explained earlier, the last 4 years we've rolled out zero defects training to our suppliers and internally in Rolls-Royce. And when we go through process FMEAs in the way we've just done, the one comment we always get is, yeah, but you struggle to give us design support, and therefore how is this really going to happen? So we said, well, we had the design exec with us on many of these conferences, and he said, well, if you don't get the response, contact me directly and I look into it. About a year later, and we were doing some more of these rollouts and this issue came up. He said, well, guess how many escalations I've had. You know, I've spoken to 200 suppliers about this, and I've given them permission to contact me if this is a blocker. And he'd only had one email in 12 months asking him to support because Rolls-Royce had said they couldn't support on the design. And that doesn't mean that everybody else has said yes, but how many times we do get asked to support is very limited. And it's really important that we don't become victims with this too. So there's still an awful lot you can do on a process FMEA without the design, right? Because you should be experts in what it is you're producing. You will have knowledge of what happens when certain things go wrong because it would have happened before and your customer would have talked to you and you'd have known that this thing caused an in-flight shutdown, or you would have known that this thing has a performance issue to the engine. Clearly, it's always best if you get a designer involved. We know from yesterday's conversation, you're only going to be asked to do FMEAs on new product introduction, where you're making a change, and if you've had a major quality escape. So if you're accepting new work and the customer wants you to do APQP, you need to be saying, well, are we going to get design support when we do our FMEAs, etc.? Because if you look into Sabre for the last 4 years for Rolls-Royce, there's always been a requirement to do FMEA and to do FMEA to AS13004. Everything we've been through today is consistent with AS13004, which has been around since 2017. So, you know, it's really important that we understand that, yes, absolutely, you need a designer to be involved. And for many of the parts, many of our suppliers take a design from Rolls-Royce. You need to be demanding of it, but don't use that. You know, the worst thing I fear to think is, oh, I can't do a process FMEA because I don't have a design FMEA. That's just not true. So do what you can. The best thing then to do is if you've got an FMEA that's complete as far as you're concerned, and you invite a design engineer into contributing towards the severities and the effects description, that's a nice, concise, well-prepared proposition for the design engineer to say, well, I'm not going to be sitting in loads of meetings for loads of months. You've done all the work. I'm going to come in and I'm going to add in my insights into that. So I agree it's an issue. I agree, you know, it needs a different way of working between the supplier and the customer. We need to get better at it, but we also need to have that signal that those questions are being asked. Since 13,004 has been raised, we've had very few requests for that. But where we have had it, and we talked about some of the best practice yesterday, so Samsuzhou in Shanghai, GKN in Newington in North America. There's two examples where Rolls-Royce Design Engineering did get involved, and two examples where we actually got to zero defects on things that had never been zero defects before. So we know it works. Is it a simple thing to suddenly start supporting it? Absolutely not. I mean, Rolls-Royce, we lost 40% of our resources last year. Of course, it's going to be a challenge. But as I said yesterday, if we don't do these things, then we will always end up having what we've got now. And what we've got now is too many escapes, too much rework, too many delivery delays. We have to do this differently if we're going to go forward. So I understand your concerns. I recognize that in some cases, it's not going to be as easy as just asking and getting the resources, but that shouldn't stop you getting on and implementing FMEAs to this standard. Okay, Rudy?
Okay, thank you, Ian.
Okay.
No further questions.
Okay. I'm just conscious of time. We are going to have to kind of speed up, but there is a section later on which is a repeat from yesterday, so maybe we'll go through that even quicker. So we've looked at the requirements, we've looked at the failure modes, effects, and severity. Now we're going to start focusing on a process bit. So this is where Process FMEA gets its name. And we're going to look at potential causes. So on this one, we've got a failure mode. The potential cause is directly related to the failure mode. Okay. So on this one, hole diameter too big. What would need to happen in the process to cause that hole diameter to be too big? And it should be as cause and effect as we can get it. I remember seeing an FMEA once on an assembly process that for potential causes, basically it just said operate error, operate error, operate error. That doesn't really help anybody. So we need to make sure that when we are putting a cause in here, it's if this thing happened, it pretty much guarantees that this failure mode is going to be the result. So things like operate error, poor maintenance, incorrect work instructions, they should not be seen in this column. Now there's a couple of other things to bear in mind. In all process FMEAs, if you go back to the automotive standards, when we're looking at the process FMEA, you have to assume that the design is right. Now, normally you say this in a room full of people and people start laughing, but you have to assume the design is right, because otherwise you just go through all the potential causes and go, oh, design was wrong, design wrong, design wrong. That is outside of the remit of a process FMEA. So always assume the things you've been asked to do, the design is right. And if you are doing assembly, you have to assume that the parts being supplied to you are correct. So again, if you just went through and said, yeah, incoming part too big, incoming part too small, that is not going to help. This should be focused on the activities of the process that you're looking at. The supplied parts, they should have their own FMEAs and they should be controlling the quality of their parts through that. And the designer has their design FMEA to make sure that that is controlling the quality of the design. So the other thing to avoid is too much detail. So typically for every failure mode, you're looking to 4 to 6 specific potential causes. But one of the things that I've seen teams fall into the trap of is actually repeat lots of different causes that are actually describing different ways or similar ways of actually causing that failure mode. So if we take our heat treatment example, we said one of the problems with material retardant, you leave it in the furnace for too long, and then you have 4 or 5 different causes. So, well, material was left in the furnace too long because the alarm failed. It was left in the furnace too long because the operator got distracted, etc., etc. They're all ways of describing the fact that the part was left in the furnace too long. That is the bit you need to know. How you stop the alarm failing, the operator distracted, that will come on later when you're looking at prevention controls. But for this one, you only need to list once. One of the causes would be if you left it in the furnace for too long. So making sure we don't just describe the same thing in different ways is one thing we've seen on a number of FMEAs. So once we've been through and we've looked at what are the causes of hole diameter too big. So in this example, we could have used the wrong drill. We've used an oversized drill, and that could be oversized from the supplier. It could be because we've used a wrong drill part number. It could be that the spindle alignment was in error, so the actual spindle when we're drilling is actually not true. Or the part is loose in the fixture, so the part is rattling, you're trying to drill a hole. All of those things could lead to the hole diameter being too big. So the next column then is saying, well, if we know that those things are true, and each of those could lead to a hole diameter being too big, how could we prevent that potential cause from happening? So a wrong drill used, we would go through and say, well, what could we do? Now, clearly when, the fact is called prevention control, it's really important that these are really preventive actions and not just things to do. So for instance, if you said wrong drill used, prevention control, train operator to use the right drill, that is not a prevention control. Things like mistake proofing, it may be, preventive maintenance, those sorts of things belong in this column. But often I see training, so potential cause, operator error, prevention control, training. They're good things to do. Training is always a good thing to do, but it's not going to prevent somebody getting it wrong. So we should avoid, we've got work instructions, we've got training, those aren't prevention controls. It's better in some cases just to write none in that box, because one of the difficulties we've seen is as soon as you put a sentence in there, when you're reviewing it, your eyes kind of pass over it and think, oh, I got something in that column. It's best either to leave it blank, write the word none, because I think 70% of the improvement actions you get out of your early process FMEAs will be, we haven't really got a prevention control in place for that potential cause. So make sure you don't be afraid of writing none in prevention control if you don't have something that really does prevent it. Okay, so on this particular one, wrong drill used oversized, well, we've got a tool presetter. So that's checking the diameter of the tool before we put it in the machine. Spindle alignment error, well, we've got a preventive maintenance schedule that includes a laser alignment check every 6 months. Part loose in fixture, well, we've designed a fixture that's got an air detection system in it. So if the part isn't sitting right, then it will actually detect it. And swarf pickup on drill, well, actually, we don't have any control for that. We know it happens. We know it can cause hole diameter too big, but there's nothing that we have at the moment that prevents that. And that's why we've written none in there. Now we can review that later on. And if that's an issue, we can say, well, what would we do to prevent swarf pickup on the drill? What sort of things can we use as the chip the score for or whatever, that could be an improvement that would really help on this failure mode. But these are specific prevention controls. And then when we come to occurrence, now this one can cause some confusion. So the occurrence score is an estimate of how likely is the failure mode to happen and or the actual potential cause. So in many cases, if you said on this particular diameter, what's your capability? How often do you make it and it's too big or too small? Most organizations are quite mature in having that sort of data. So you can say, yeah, it's 5% fallout because of this or 1%. So describing the overall failure mode likelihood of occurrence, most of us are pretty good at. When it comes down to, well, how often do you have an issue with the drill being oversized or the spindle being the cause of the error? Those things are much harder to try and describe and try to put a number against. So we use the rating table in a way to answer those questions. This is the rating table in 13004. And what you see again, it's a rank of 1 to 10. But 10 is, everything you make is going to be wrong. And 1 is it's never going to happen. And then you have obviously different degrees between 1 and 10, from never happened to always happens. Now it's described in a couple of different ways. So you've got a PPM, process PPM. You've got a likelihood of it happening. There's a time-based example. So if it was a failure mode issue, you might describe it in likelihood of process PPM. Time-based example, if you were looking at, well, how often does my machine go to calibration, then maybe this would be the best way of looking at it, because it's once every 6 months, once a year, etc. So you've got some different ways of assessing it. I'll come back to low volume in a moment, but the intent is trying to give a relative score to how often is this thing going to happen. Not in 13004, but included here, there's also a CPK lookup, so you can convert your PPM and your likelihood into what CPK you have. The important thing to notice is a CPK of 1.33, which most people see as the threshold of acceptance on key characteristics, only gets you to a 6. Okay, so you may have a CPK of 1.33, it's only going to get your occurrence rating to a 6. You need to be a 2 or more, get down to a level 2 on the ranking. So you need to bear that in mind in your relative rating too. That is quite a difference to what we see being used in practice today. So one of the things, we want an RPN score for every cause. But when you first do your process FMEA, you may struggle to get an accurate score for part loosen fixture, spindle alignment error, wrong drill used. So one of the proposals in 13004 is you can use your whole diameter yield, CPK, to give you an estimate of the score that you can use for all 3 of those different potential causes. Because overall, you've got a CPK 1.33, gives you 5,000 ppm, that's a 6. If when you've scored it all and you've done your RPN and it's a high severity issue, or high severity terms occurrence rating, then you might say, well, I need to understand this in more detail. I need to find out, is it my spindle alignment that's causing the problem, or part loosen fixture causing the problem? Because I need to drill down into a different level of detail to find out why this is happening, because it's a high severity occurrence. So the first pass, you might use the data you have on failure mode. That allows you to say, well, where's the high severities, where's the high RPNs, and then you would go back and explore a little bit more detail about individual potential cause scores. Okay. Low volume, I mean, I know when I joined Rolls-Royce from automotive, everything seemed low volume. What this is really trying to get at is this is where you may have parts that are now in service. You're making one batch a year. It's not continuous production. It's what they call an alien and a stranger. So you haven't made it for 5 years. You're going to make one or two, and therefore, you know, it's going to need some sort of different statistical estimation because it's not a regular thing. But it is for development parts or for spares. It shouldn't be used on normal volume production. Okay, so that's section 3, looking at occurrences and prevention. And the big thing to take away, prevention needs to mean prevention. And that's one area where I think we can all kind of strengthen our definition of what belongs in a prevention control. Detection is quite simple. So a detection control, just go back. So a detection control is linked to either the failure mode, or it could be linked to the potential cause. So what most requirements and failure mode should have an inspection of some sort, unless you're onto sample inspection or reduced inspection because your customers allowed you to do that. So you would expect to see for every potential cause, when you score the RPN, you have a detection control that includes inspecting for the failure mode. And in this case, we've got a CMM check at op 450 that will measure that hole diameter. Okay. But for spindle alignment, if you notice, we've also got something called a ball bar check that the operations team carry out every week. Okay, so it's not preventative, but it's just a check to make sure that the alignment is still within limits. And then finally, for part loosen fixture, apart from the prevention control we got, the only other way of finding it is that CMM check and op 450. So the detection controls should list both failure modes and potential causes where they exist, but you definitely should have a detection control for your failure mode. Again, there's a table in 13004 rated from 1 to 10, where as you're going to manage, 10 is you're never going to find it. If this failure mode happens or if this cause happens, there's nothing we do that will actually find it. Also included in there, which is important, if you haven't done an MSA to prove out your inspection capability, then that's put in as a 10 as well. And that's going to be quite, that's going to expose some gaps, I think, in many organizations. A 1 is detection. You don't need to look for it because it's mistake proofed. You can't actually make the non-conformance in the first place because there's a mistake proof process that won't allow that non-conformance to be created. And then we've got a list of descriptions in between. So, you know, the 2, 3, and 4 are all methods of automated inspection. You're either looking for the failure mode, or you're looking at detecting the failure mode. But it's all automated. You know? So these are things where it's mistake proofing, where you're not relying on human inspector to measure something or to visually inspect something. Which means that for anything that does need measurement by a human or inspection, the best score you can get is a 5. And that's really important because I see, you know, one of the things sometimes you get a lot of low RPNs. We've scored detection as a 2, but it's actually based on a visual inspection by an inspector. So the next block says, well, 5 is if you're inspecting where you create it, where you create that characteristic, using a variable means, you score a 5. A 6 is if it's after the event, so it's further down the process. that you're looking for it, then it's a 6. A 7 is attribute, either at source. An 8 is post-processing. So you can see here 1 to 4 only for automated inspection from the A level of mistake proofing. 5 to 8 you can make adjustments based on where you inspect it and if you're using variable or attribute. 9 and 10 difficult to detect, or definitely uncertain because you're not inspecting it. So we're going to run a poll. Let's see if that makes sense. We have 4 detection controls. Let's have a look at the description and see if we can get the scores right. So the first one, Becky, we're going to look at this top one, CMM check at op 450. In other words, post-processing. We're making this at op 10. We're not inspecting it until op 450, and we're doing it on a CMM. So it's a variable measurement. Okay, Becky, can you run the poll?
So the poll is open, everyone. Go ahead and enter your vote into the Slido poll, and we'll give you about 15-20 seconds here to vote. Looks like everyone's starting to vote. Looks like a close race between 4 and 6, maybe. A few more seconds, everyone.
Yeah, I mean, don't forget, you can't get better than a 5 without automation.
So the results are showing, oh, sorry, Ian.
Yeah, sorry, Becky, go on.
The results are showing about 31% for number 4, and for number 6 we have 51%, with number 8 showing 8%, and the others are smaller.
Okay, so the first one is a 6. So why is it a 6? You're measuring it with variable gauging, it's a CMM, but you're measuring it post-processing. So it's not in the operation where it was created. You're allowing that part to travel further through other operations before you measure it. So to be a 5, you would need variable gauging, but at the point it was actually created. So it's in the station by the operator using variable gauging. This isn't in station, it's post-processing. So that immediately takes us to a 6. You know, a 4, I saw some, you say 4, 31%. To score a 4, you'd need defect failure mode detection post-processing by automated controls that will detect the discrepant part and lock the part to prevent further processing. So that is, you know, that is a inspection method which, as part of the process, means that it's kind of error-proofed because you can't allow it to proceed because it's actually going to do something to lock that part. Okay, so this scores a 6. So for everybody that got a 6, well done. The next one, vernier check by the operator in the cell at op 100. Okay, so this is it in the cell where it was created. It's a vernier check by the operator. Becky, if you run the poll, let's see what we get.
Okay, the poll is open, everyone. Looks like we have a few votes coming in. So again, we'll give this about 20 seconds for everyone to submit their vote. A lot of responses on number 5 there right now, but number 7 is also gaining some ground. So about 10 more seconds. Okay. So number five has 69%. Number 7 has 21%. And those are the highest ranks. Everything else is 1 or 2%.
Okay. So in this case, you've got the operator using a vernier. So it's a variable measurement in the cell where the part was created or the feature was created. So in this example, that's going to be a 5 because you've got detect the failure mode or the cause in the station by the operator through the use of a variable gauge or automated controls. Well, in this case, it's a variable gauge. So this one, for everybody that scored it as a 5, you're right. But it shows that, you know, by bringing the inspection process closer to the point of feature creation, it reduces the risk of actually missing it. So it's a more effective control. Okay, what about this next one? CNC ball bar check. So this is done every week by the operations team. They basically run an artifact just to check if the spindle alignment is actually okay. So Becky, if you run the poll.
Okay, the poll is open, everyone. We have a few votes coming in, so let's give it about 20 seconds here, and we will call the results. Another 10 seconds or so. So right now it looks like number 2 has about 19%. Number 3 has 8%. These are pretty spread out. Number 4 has 5%. 5 has 7%. 6 has 6%. 7 has 15%. 8 has 12%. And number 9 looks like a winner here with 22%.
Okay. Well, let's take a look. There you are. And it is 9 because if you look at difficult to detect, in this case, it's difficult to detect the error cause. Random audit is effectively, you know, this is a check of the spindle alignment once a week. It'll tell you that you've got a problem maybe, but it's not proactive, and you know it's somewhere, I guess, between a you know, an 8 and a 9 in terms of effectiveness. I wouldn't like to rely on it, but it gives you some information. So we've actually scored it as a 9. But then last one, CNC in-cycle probing of diameter. So this is where you have a CNC machine. As it's actually machining the part and doing the different features, it has a probe that goes in and is used as part of the machining cycle to pick up on reference points, to confirm certain features, to make sure that it's conforming, but it's done as part of the machining process. Okay, if we open the poll.
Okay, the poll is open, everyone, so go ahead and submit your vote. Again, we'll give it about 20 seconds here for everyone to review and click. So about 10 more seconds. Looks like we're getting quite a few votes. So number 2 is showing about 26%. Number 3 is showing 55%. And then we have number 4 with 6%, number 5 with 8%.
Okay. That's good. So 55% had number 3, because if you read the description, 3 is you're detecting the failure mode in the station, automated controls, you're not relying on the operator to do it. to detect non-conformance or discrepant part, and then lock the part in station so that it can't be processed further. So you can see from this, the way the scoring drives you is, first of all, if you can do the check in station rather than after the event, whether that's error proofing or inspection, you get a better score than if you leave it and inspect everything at the end. And this is really important, because I think when you're designing your inspection plan, for certain things with high severity or high occurrence, to lower your RPN, put in the inspection actually in the station can be really important. It'll lower your score, it'll reduce your risk, because if you think you make a batch of parts and you put all your inspection at the end of the process, you would have processed all of those parts and then found out they were wrong. You may not do it for every feature. There's some features that you've got high capability, never causes you a problem. You might decide to leave those for your final inspection at the end. But for certain things that are marginal capability, or you do get problems, you may want to put that inspection right next to the process or actually in process. And the other thing it talks about is variable versus attribute. Why is variable better than attribute? Well, for variable gauging, you have a chance to kind of look at your trends, and you can actually make an adjustment before you make non-conformance. Whereas with attribute inspection, all you know is it good or bad, and it can take you by surprise when it suddenly goes to be non-conforming. So variable is always better than attribute. In station is always better than post-processing. So mistake proofing is always the best. There is so many different low-cost solutions now to mistake proof either the cause prevention or the detection of it. That's where the FMEA should be driving our processes. Remember, without automation, without a level of mistake proofing built into the process, you can't score lower than a 5. So as soon as you're relying on an inspector to measure something or inspect something, the best score you can get is a 5. End process better than end of line inspection, variable better than attribute. And the other thing it talks about is boundary samples. So in automotive, this used to be one of the really key things for our inspection areas, that there were always boundary samples. So what was good, what was bad, but more importantly, what were the things around the threshold of good and bad? What was just okay and just not okay? To help the inspector make decisions. And that is reflected in the scoring guidelines here. So if you've got boundary samples, you will get a better score than if you don't have boundary samples to help with that inspection. And if you haven't got an MSA, then you're going to score a 10. If you haven't passed an MSA, then you're going to score a 9. So having knowledge of, does your measurement method, is it capable, is really, really important. Okay. So that brings us kind of to the end of what we're going to cover. No, actually it's not. If you bear with me, there is one other thing I just wanted to cover quickly. We covered this yesterday. So in terms of scoring the RPN, severity, occurrence, detection, very straightforward. I think we've seen today now, actually you'd expect multiple effects, multiple causes, and potentially multiple detection controls. So when you score on the RPN, in this situation, you've got to choose the highest severity. You'll have an RPN for every potential cause. So it should be every occurrence score is used, and then the best or lowest detection. And from the examples we've seen today, I mean, if you have error proofing in place, it might give you the opportunity to remove some of the downline inspection, because over time we've put different types of inspection in. If it's error proofed, maybe there's an opportunity to take some of that out. And now you multiply it, so 8 times 5 times 5 is 200, 8 times 8 times 2, 128, 8 times 3 times 3, 72. And improvement actions, again, we covered this yesterday, but it's not just about working the Pareto. Concentrate on high severity scores, combinations of high severity and occurrence, and then high RPN scores. This prioritization matrix is a really great way to take those scores from your FMEA and show you where you need to be focusing your improvement. Severity can only be reduced through changing the design. Occurrence can only be reduced if you mistake-proof it or improve your process capability. And we've just been through detection scores, so use of error proofing or variable inspection at the point of feature creation will get you a better detection score. In the first example we saw yesterday, to lower this RPN of 216, what Sarah's done is move the inspection from post-processing to in-process. That got her to reduce the detection score from 6 to 5. And what Darryl did is he increased the frequency of preventive maintenance on the laser check-in, which reduced the score from 4 to 3. So we've gone from 216 down to 135. Now, one great way of going through and evaluating your own FMEAs, now that we've covered yesterday and today, hopefully this will make sense. These are the questions you can be asking. So, have I got all of the operations and steps included in my FMEA? Do the requirements describe the desired physical properties of the product to be achieved? Do the failure modes describe the physical properties of the product and how they fail to meet the requirements? For effects, does it include how it impacts the customer and end user as well as the internal impacts? Severity scoring, does it use the guidelines in 13004? Or is there a customer approved alternative that you have? Are the potential causes, are they real potential causes? Are they cause and effect? Or are they quite loose descriptions? Same with prevention controls. Are they really preventative or are they just stuff we do? In other words, training, work instructions. Recurrent score using 13004, detection scores, detection controls, do they include both failure mode and the potential causes? Have you used the scoring for 13004 for detection? And have you scored the RPN using the example we've just been through? So that's just a way of kind of evaluating how compliant to 13004 are your FMEAs today. And just to run a quick poll before we go to last questions, we asked this yesterday. Now we've been through in more detail today. I'm just kind of interested to see if those scores have changed in any way. And just picking up on a lot of the chat that was there, I can see there's some questions being asked, which may suggest that there are some differences of opinion compared to where we were yesterday. So Becky, would you like to run the poll, please?
So the poll is open and I see that people are starting to vote. So let's give it about 15 seconds here and we'll get some results. Another 5 seconds, everyone. So it looks like 10% for not at all. We do not do process FMEAs or control plans. 22%, it is very different to how we currently do it. 57%, we comply with more than 75% of the requirements, but there is more we need to do. And 13%, this is how we conduct process FMEAs and control plans.
Okay, good. So there's been a slight shift there then, so that's to be expected, I think, as we've gone through the detail today. So, having gone through the material, there's now an opportunity for questions on anything we've covered this afternoon. So I'll just give Rudy a few minutes to look at selecting a couple of questions. And as Rudy said earlier, we will answer all questions that have come in on the website, but if there's a couple of key ones now, Rudy, we can cover.
I think so. I think we can cover a lot of questions here. So we have received indeed a couple of questions here, and one questions or several questions are concerning the occurrence ranking. For example, the occurrence table. At what number are we talking about? Low volume or high volume criteria? Is there a limitation value?
Yeah,
that separates.
That's a great question. There's not it's not clearly defined around volume of parts, etc. I think the way to think of it, as I tried to put in the slide here, is if it's a development part, I think it's legitimate that you could use the low volume. If it's a non-routine part, so it's not part of your ongoing production, it's a spare maybe, it's something that you're asked to make but really infrequently, then you should use it. I'd say for every normal production part that you create, you should be using the standard scoring criteria. Be very careful about using low volume, because low volume in the context that was meant was for special batches of things like development parts and things, not for ongoing production. I guess the only thing I think to add to that is, because the scoring is relative, if you did use the low volume throughout an FMEA, it's still going to give you a relative scoring on your RPN numbers. So as long as you're consistent with it, then it shouldn't really change the risk profile that you will end up with. So I would always steer away from using the low volume criteria, but there may be some genuine cases where you could say, yeah, it actually makes more sense. But if you're going to do it, be consistent throughout the FMEA when you use that scoring guideline.
Okay, Ian, thank you very much. So next question was, do we need to score the occurrence of every course or only of the potential failure? RM13004 shows the score against every course.
Yeah, what I tried to explain on the chart, and maybe I went through it a bit too quickly. It can be very ideally, the ideal scenario would be for every cause you would have a score. The reality is, when you first put your FMEA together, a lot of those potential causes will be quite hard to determine how often it actually happens. Okay, and therefore, on a first pass of the FMEA, what we've said in 13004 is use the score you would get from the failure mode, and you can use that for all of your potential causes, right? So let's say in our example we shared this afternoon, we had failure mode as a 6 because it had a CPK of 1.33, and we used that for each of the 4 potential causes we identified. If later on, and you come to do the RPN, or you look at it and it's got a high severity, an 8, 9 or 10 severity, and you don't understand, well, what is the individual potential cause frequencies, you may want to go and actually find out that data. So if you imagine that hole too big, if that led to a potential for explosion or engine fire, and you didn't know how frequently the 5 potential causes you have occur, how would you choose what to go and look at to go and improve? So the simple answer is, if you've got the information, you should include it on your first pass. If you don't, most people should have the information for at least the failure mode and how often that happens, or the CPK or whatever. If it comes out as a high severity or high severity times occurrence score, you want to go in, and one of your actions would be to find out relatively what is the main cause of that failure mode actually happening. Okay.
Okay, Ian. Our next question was, how could I improve my detection system if my inspection methodology is only visual inspection? In fact, the visual inspection rating falls between 7 or 8 ?
Yeah. So we know, visual inspection is a particularly unreliable way of guaranteeing that only good things pass on, or we select good from bad. So I think it's a reflection of relatively how much reliance would you put on a human inspector being able to find non-conformance if it happened. And therefore, if you're inspecting the part and you're wholly reliant on a human inspector to inspect something that's got a very high severity, you should be looking again at what can you do to improve that. Can you put some sort of mistake proofing in? When you're looking at a whole engine, you have thousands of clips and things that need to be in position. Asking a person to try and review all of that and find the one which is slightly out of position is just beyond the capability of any human to do that. So you would look and say, well, how do I take that out of the equation? Are there camera systems I could be using? Are there other ways I can guarantee that is right? So I might look at, how do I put the focus on the error cause instead of the failure mode? Are there ways we can mistake proof that when we put it together? So the fact it scores high is not by accident. It's because we know human visual inspection is particularly unreliable. Now, if it's a benign feature that rarely happens because the occurrence is really low, maybe you can live with that. But as soon as you get, high occurrence, high severity, it's going to force you to say, well, I need a different strategy for my inspection. Otherwise, if these things happen, they can have a really bad consequence, and I'm relying on, my friend in inspection to catch it. That is not fair. It's not fair to ask somebody to do that. So it should really challenge us. But one of the things with FMEAs is, if you do an FMEA and you don't end up changing anything, you probably haven't done a very good FMEA. These are the sorts of questions that I think a lot of us find when we do an FMEA. Is our inspection good enough? Have we mistake-proofed everything we could mistake-proof? Did we understand what the severity was? And if we did, would we actually change how we make it, how we inspect it as a result of that? And when we launched our Zero Defects program in Rolls-Royce, the measure of success wasn't, have we got to zero defects yet? The measure of success is, what have we changed in our process or about our inspection to improve it? So we would expect the process FMEAs, if they're done correctly, to drive process improvement. And if it doesn't, what's the point of doing it? Because, as I said yesterday, today's level of performance across the supply chain to our customers is not good enough. We are looking for a step change in quality performance, and this is one of the best methods that we can deploy to give us that step change. So that type of question of, we use visual inspection, it's scoring a 7 or an 8, that's going to give us high RPNs. Yeah, well, that's great, but that's a great discussion to be having within your business. How are you going to lower that? Okay.
Okay, Ian. One of the next question was, does AQL level, acceptance quality limit, I guess, or sample checks affect the detection ranking? I think it's meant, is there a big difference between a 100% inspection or a sample check or an
I guess
AQL level?
I guess when you get to an AQL level, you're assuming you've got a level of capability from your process that's allowing you to inspect less. So you would expect only to be applying AQL levels where you have a high capability and therefore a low occurrence on a particular problem. The inspection methodology doesn't, or the inspection scoring doesn't take account of AQLs and sample inspection. For AESQ, there's a different reference manual that discusses that, but you would only apply sample inspection where you have high capability, and therefore how many parts you need to inspect is a function of a different process. In our case, it's RM 13002. But it wouldn't make any real difference to how you score this, the way it's written today. And I think that's the same if you look at the automotive books, etc. It doesn't take any allowance of, is it 100% or is it less than 100%? Okay.
Okay, Ian, thank you. Next question was regarding key characteristics. If we didn't have key characteristics from our client, do you have an example how to fix our KPCs?
If we didn't have a KC from our customer, how do we fix? Sorry, I don't quite understand the question.
So I think it's meant when there are no key characteristics are provided from the customer to the supplier. So what should the supplier do?
Okay, key characteristics can be what we call a sort of a red herring. It can be a distraction. We've talked about the fact that the FMEA covers all characteristics. And I know in the past, companies like Rolls-Royce have said, well, we're going to do MSA only on key characteristics, or we're going to do FMEAs only on key processes. Well, 13004 says, no, you're going to do all processes, you're going to do all characteristics. The part, if a customer says to you, but these 5 characteristics are absolutely key because of safety concerns, the purpose of that is when you do your FMEA, you're expecting to see that flowed into how you do the scoring. So for instance, the severity score you'd expect to see reflected because it's a key characteristic. The occurrence score, you're going to look at, well, if it's a key characteristic, should I be mistake proof in this? How critical for safety is it? In many cases, a customer might have a different level of capability for a key characteristic to non-key characteristics, so it might be a CPK of 2, whereas everything else is a CPK 1.33. So having key characteristics identified may lead you to score things slightly differently or have different considerations how you control it in your process control plan. But it's only a subset of the fact that, well, on this approach, you have to do all characteristics anyway. So whether or not your customer tells you there's a key characteristic or not, it doesn't change the fact that you're going to work through the entire drawing and do an FMEA for all characteristics. the fact that it's defined as a key characteristic will just highlight certain things which should be picked up in the effects and the severity scoring when you're doing that anyway.
Okay, thank you, Ian. Another question was, could you please explain the definition how to generate the RPN value? What is the RPN value and how is it defined?
Okay, so the risk priority number is simply your severity score times your occurrence score times your detection score for a particular failure mode and potential cause combination. So every failure mode and its potential cause will have a risk priority number based on severity, occurrence, and detection. We know there's going to be multiple effects, so there'll be multiple severity scores. Each potential cause will have an occurrence score of its own, and there may be multiple detection controls that you would score. So in this example, we've got 3 potential causes for this one failure mode. So we would expect to have 3 risk priority numbers. So how do you choose which score to use to generate that when you have more than one? And what we say is for severity, you always choose the highest severity score. So the worst thing that could happen, that's the one you use. You then use each occurrence score that you have for each potential cause. And then for each potential cause failure mode combination, you choose the lowest detection score for that combination. So in this example, you're going to take the highest severity, which is 8. And for the top potential cause, it's 8 times 5 occurrence times 5 for detection. And that's going to give you an answer of 200. For the second potential cause, you're going to take the same 8 for severity times the 8 for occurrence multiplied by the 2 for detection. That gives you an RPN of 128. And finally, for the last potential cause, you've still got 8 for severity, 3 this time for occurrence, times 3 for detection. Multiply those 3 together, and you get the 72. And that allows you then to kind of build a risk profile of what are my biggest risks by multiplying those together. However, using such a simple RPN score to say, well, what should I do first, isn't always the best way of doing it. And therefore, the recommendation is you would pick on high severity items or high severity times occurrence. And that's why this grid is seen as quite important. Many companies use something like this to kind of plot all of the different RPNs against, or all of the different severity and occurrence scores against, to use this to prioritize where to take those actions. Does that hopefully explain how RPN is done?
Yes, right, yeah.
Rudy, I'm just looking at the time. We've only got a few minutes left.
Yes. Okay, then I jump over and I have a general question here. Just let me see. Are the slides from yesterday's session already available?
No, we have to create some PDF versions of it, and to do that, because of the animation in it, it's going to take a little bit of time to recreate some, so that the animation doesn't become a problem when it's just a PDF slide. So like with the videos, it'll probably take us a week or so to do the editing to allow us to have a pack that we can put on the website and share.
Okay, thank you, Ian. Then I will finish the question block for today.
Okay.
Thank you very much.
So just a couple of final slides before we leave it. Reference Manual 13004 is available free of charge from the AESQ website. You can download it. Everything we've been through yesterday and today is in this reference manual with examples and with a bit more detail of how to do it. But it's there, you can download it, you can do as many copies as you like. The SAE do provide training aligned to 13004, and that's available globally. And it includes things like the reference FMEAs we're going to cover tomorrow. It includes design FMEAs and control plans. So everything we've talked about and the other tools that are in 13004, the SAE training course is available. And there is a subject matter interest group where Rudy and myself and a team from across the AESQ companies are looking at what we can do to support deployment of this across the external supply chain. Because, you know, we need everyone to be successful for us to be successful. So that's why we're doing free events and providing free information, etc. We see this as a really important part of making a step change in quality performance within aerospace. So the subject matter interest groups, if you type in AESQ into Google, it'll take you to the landing page on the left. At the top, you'll see activities. Click on that, it'll take you to the interest group landing page. At the bottom of the landing page, you will see all of the subject matter interest groups that are set up. We're under Defect Prevention Quality Tools for APQP. Click on that and it takes you to our own page. That's where you will find these videos when we put them online. That's when you're going to find the slide packs and any other information. But there's also a contact link on there as well. So you can send us an email. You can request, you know, what can we do to help you deploy this in your organization? What other things should the AESQ be looking at to allow you to deploy this effectively in your business? So please take a look. It's updated on a regular basis with different tools and different information resources, easy to get access to. But, you know, let's start a dialogue of what do we need to do to do this effectively. So that takes us through session 2. I hope you found it useful. Session 3 tomorrow is going to look at reference process FMEAs. So if you want to know how to maximize the efficiency of doing this, build on previous learning, and do this in a timescale that allows us to do with a small focused team, reference FMEAs are going to be really key for that. And then also we're going to look at, once you've created your FMEA, how can you use that to generate your control plan? And again, with certain software, it can do that automatically once you've got your FMEA in it. So again, we'll look at that tomorrow. So thank you for joining. Thanks for all of the questions and the comments. Particular thank you from me to Becky and Rudy for helping support us through this, and for the SAE for making all of this happen and making it available free of charge. So I hope you found it useful. I really hope you'll join us again tomorrow for the last 2 subjects. But I'll draw it to a close there. Thank you much. Thank you very much. Cheers.
Thank you. Cheers. Have a nice day. Nice evening. Bye-bye.